Alright guys, so today I'm going to start your learning about circular motion. Alright, and so I'm going to actually start you off with a question. Alright, so take your time, answer this question. Race car is driving around a circular racetrack with a constant speed of 100 miles per hour. The car is... And take a minute, pause it, think through the question, convince yourself of an answer, commit, and then go ahead and unpause it and get the answer. Alright, so by now you should have answered. The answer, of course, is that it is accelerating. Now you have to remember that this is because if it's going around a circle, even at constant speed, it was very important here that it says constant speed because the velocity is changing, right? Because velocity is a vector. So at the top, I'm traveling this direction. At the side, I'm now traveling this way. My car is always changing direction. If it's always changing direction, then your velocity is changing. And if your velocity is changing, that means it's accelerating. So you need to remember that acceleration means a change in direction, all right? So any circular motion means that your object is constantly accelerating, whether it's changing speed or not. All right? So here's a couple of things that we know travel in circles. You got fairground rides, you've got the moon going around the earth, you've got this rock on a string being swung around, all right? So these objects are often at constant or close to a constant speed, right? But what does Newton's first law say? Well, Newton's first law says that an object will maintain its state of motion, meaning that it will maintain its current velocity, both magnitude and direction, unless a net force or unbalanced force causes it to change, unless something else makes it change. Okay? Now, in all of these situations, whether it be the fairground ride or the moon or the rock sliding around, these objects are not maintaining their state of motion. So in order for them to change their state of motion, to change direction, there must be some kind of force acting on them. Okay? There must be something else that's causing them to change whatever they're doing. All right? And so we're going to talk about that a little bit more today. But first, a little bit of maybe nature of science, theory of knowledge. How do we know the Earth is rotating? Okay, go ahead and pause the video. Think about this for a couple of minutes and then unpause it and I'll talk about that a little bit. Okay, so hopefully you've kind of thought about how we know it's rotating. A lot of times people say, well, we look up at the stars, but that's not really valid because the stars could be moving, right? We only say that we're moving under the stars because that's what we've been taught. So how do we know the Earth is actually rotating around its axis and it's not just the rest of the universe that is moving? Well, the best that we can do is something called, at this level, the best we can do is something called a Foucault pendulum. Okay? So a Foucault pendulum is set up as in this drawing right here. And what it does is it has a very, very long string or rod, very light, and then at the end it has a very, very large, very massive ball or whatever at the end. Now, what happens as it swings is that it swings very slowly. And as it swings over, if the ground is rotating, because of the length of the string, if the ground is rotating under it, then when it swings back, it's actually going to swing back in a slightly different location than where it started from, because it will maintain its forward and backward momentum, just going forward and backward. And so if the ground moves under it, then it will actually rotate. And you'll see this kind of diagram like the star where it starts here and it goes that way and then it comes back and then it goes over and then it comes back. And so it slightly moves every single time. Now, on Earth, it takes us about 24 hours, though it's technically not 24 hours, it's a little bit less. It's a sidereal day. But we don't need to worry about that now. The idea is that it would take approximately 24 hours for this star pattern to go all the way around to where it started again. All right? Now, of course, that would work very nicely at the North Pole, where the Earth is actually rotating in a circle around it. Anywhere else on the Earth, though, you can still do this. It's just the effect is not as great. It might take it longer than a day to get all the way around. And so that has to do with your latitude. And you can read up on Foucault pendulums if that's interesting to you. But that's an important idea because that's a way that we can see that force associated with the spinning, the turning, the motion. All right? Anyway, back to circular motion. So we're going to actually start to put a little bit of math with this before, I guess there's a little bit of math we need to understand before we start really talking about those forces that are causing this circular motion. So the first thing you need to know about is something called radians. Okay, well, first, let's talk about this. Why exactly are there 360 degrees in a circle? Who in the world came up with this number, 360? I mean, why? And you're going to say, well, because a right angle is 90 degrees. Okay, well, why the heck is why is right angle 90 degrees? Why can't it be 100? Wouldn't 100 be nicer? Right? Or, I don't know, there's a lot of numbers you could come up with that would be nicer than 90. Okay? So why 360 or why 90? Well, the answer to that is that these degrees were come up with by the Babylonians. Okay? So a long time ago. And what they noticed is that the Earth took about 365 days to go around. And so they said, well, let's just say that each day the Earth goes approximately 1 degree. Now, 365 is kind of an ugly number and difficult to work with, and so they said, well, I could make it much nicer by calling it 360 degrees. It doesn't match up with days anymore, but you got 360 degrees. That splits to 90. You got the 30, 60, 45. You got a lot of nice numbers in there that end up working well with the mathematics, though still slightly annoying because 360 has nothing to do with the circle itself. 360 has something to do with the Earth, right? Which that number never would have been come up with on some completely different planet. And so it's fairly pointless. So we have something that we call radians. Okay? And I don't know how much you know about radians. So I'm going to go into a little bit of detail just so that you understand. Okay? Radians are a measure of an angle. Okay? Just like degrees are a measure of an angle. Okay? 1 radian is the angle that you have to go through in order to cover a distance of 1 radius. Okay? So if theta is 1 radian, and we can show that with a 1c, or you just put a 1 radian is the angle required, again, to go through a length of 1 radius here on the circumference of a circle. Now, you can probably figure out how many radii are there as I go around the circle. Well, you should know that the circumference of a circle is 2 pi r. Now, if the circumference of a circle is 2 pi r, that means that there are 2 pi radians in a circle. So I would go 1, and then I'd go another theta, and then I'd go another theta, and then I'd go another theta. I know I'm not drawing these very nice, so I'd go another theta. That would be another r, right? That's the length of the radius. So I got 1, 2, 3, 4, 5, and then I'd get 6, and there'd be just a little bit left. Just enough because 2 pi is about 6.28, so just enough for that to be 0.28 radians. All right? So we can get from this, because we understand that the circumference of a circle is 2 pi radians, that there are 2 pi radians in a circle. So 2 pi radians is equal to 360 degrees. All right, those two mean the same thing, 2 pi radians or 360 degrees. Now, it's common to not put any notation for the radians. You could just write this 2 pi equals 360 degrees, and that's normal. There's nothing wrong with that. That's just how it goes, okay? So we'll talk a little bit more about this later, but it's important that you recognize when we talk about radians what a radian is. It's just a degree. It's how far we're going, and we'll talk about these things a little bit more later. All right? So let's go on to the next little bit here. All right? So with this idea of radians, we're now going to talk about angular motion. All right? So first we're going to talk about angular displacement. So angular displacement is the angle through which an object passes during its circular motion. So if I have, going back to the beginning, let's say that I have my person here, and they're playing with their rock on the string, and the rock swings around this far, the angle that it has gone through, that is your angular displacement right there. Okay? So we have our angular displacement. That's just the angle that it's gone through. It's not a length, it's the angular displacement. How far has the angle gone through? Now, you can recognize that as you go around, you could go all the way around the circle from the beginning, and when you got back to the beginning, you would have traveled a distance of 2 pi radians. However, you would be back to where you started from. Okay, so your overall displacement is 0, though you have rotated through 2 pi radians. And we'll use both of those ideas later on. Next, we want to talk about angular speed. Well, you know that speed is just distance or displacement over time. And so we're going to define the angular speed. Angular displacement is just theta. How many radians have you gone through? It's very rare that we talk about degrees here. Okay, that's why it was very important that we talk about radians in that prior page. So we'll talk about an angular displacement in terms of radians over, and then when we calculate the angular speed, it's just your angular displacement over time. Or in other words, average angular speed, which is omega here, this is a lowercase omega, equals our angular displacement, which is theta, that's the angle that it's rotated through, over time. All right? Now, that will give us how many, if you look at the units, if we put our angular displacement in radians and our time in seconds, that means that it will be telling us how many radians per second we're going through. All right? Now, this, of course, leads to a couple other things which we'll look at shortly. But first, I want to talk about a couple other small topics, namely angular velocity. You notice that we defined this as being the angular speed. And that's very, very important that we're defining as a speed, not a velocity. You actually don't have to worry about angular velocity in the core of this course. You do talk about angular velocity when we get to the option, the engineering option. And you may look at that later if you choose that option for your IB. But otherwise, you don't have to worry about angular velocity. The thing with angular velocity is that angular velocity is the result of a cross product. And those who are in math may have found out that a cross product results in a direction that's perpendicular to what you're doing. And we'll talk about that more later, but it's perpendicular to the direction of your motion and the force, and so it actually ends up being completely out of the plane of motion, which makes things a little bit interesting. We'll talk about that more if we get there later. All right, so let's just double check really quick and make sure that we're understanding our ideas here. So we've got Big Ben, though technically this is not right. Big Ben is actually the bell inside Big Ben clock. So we'll talk about the clock on Big Ben and a little alarm clock. You can see the little alarm clock down here, right? There he is. Isn't he so cute? Oh, my pencil's not working. Oh, there he is. There's my little alarm clock. Both keep perfect time. Okay, exactly in correspondence with each other. Which minute hand has the bigger angular velocity? Go ahead and pause the video and think about it. When you unpause, I'll give you the answer. All right, so you should have chosen an answer. Please make sure that you're actually taking time to do this. It's very important for your learning and for your understanding that you take time to try to answer the question and commit to it before you move on. So now that you've chosen an answer, we'll give you the answer. A lot of people think that Big Ben is going to have a higher angular velocity or angular speed. This should say speed. That's not true. The angular speed depends on how fast of the angle you're going through, right? Angular speed is theta over time. Sorry, not r. Theta over time. And you'll notice that in the same amount of time, both clocks will go through the same rotation, their minute hand, right? They'll go from the time to quarter passed in exactly the same amount of time, and the angle that they pass through will be exactly the same. From 12 down to the 3, they'll both go through a 90-degree angle, which means that they're going through, or not 90 degrees, we're using radians, so that'll be pi over 2. And so the angular velocity for both of them, the angular speed, will be the same. Now, we're not talking about directions, so don't worry about the fact that it says velocity instead of speed too much, but they will be exactly the same. All right, let's try another one. Read the question, pause the video, and then unpause to get the answer. All right, so here the key is recognizing that as this rotates, it's going to cause the belt to move, right? So when this rotates, it's going to go that distance right there, okay? So it's going to go all the way around, which means within that amount of time, it's going to go 2 pi radians, right? All the way around the circle in that amount of time, that specific amount of time. Now, that means that the belt itself will travel that far. Now, you can tell on the bigger circle that that distance is not going to be very far, right? We don't know the exact ratio, so we can't really say how much farther it will travel or how much less of an angle it'll go through. But if I take this length right here, one time around, and stretch that length of belt over here, because the belt can't go faster on one wheel than it goes on the other. The belt has to travel the same distance, the same speed. So you can see that the angle here is much less than the one over there. If I were to estimate, this is about pi, so maybe if I estimate about 2 over 3 pi or something, that would probably be my best guess as to the angular displacement. Same amount of time. Of course, that means that WL is going through is much smaller, right? Your angular speed or angular velocity is going to be much, much less. And so, therefore, our answer should be B, that the angular speed of WS is much greater than that of the omega L. Okay, I know I said W, it doesn't really matter. Same thing. All right, let's go on. Okay, so let's look at a couple other terms that are associated with that. The first is period. Now, you should be somewhat familiar with period already. Period is the amount of time that it takes your object to go around the circle one time, right? So period is just an amount of time. All right? Now, of course, if we're thinking about that, we can then relate it to this, right? So period is time to do one rotation. 2 pi is the angular displacement, the amount of time, the amount of angle it has to go through for, again, we're talking about one rotation for the period. So the angular speed, remember speed is just theta over time, or in other words, the period is 2 pi over your angular speed, or angular velocity. Okay? So in this case, we'll go ahead and recognize that the period is equal to 2 pi over omega. All right? The other thing that we want to talk about right now is the frequency. Okay? So the frequency is how many rotations it goes through in 1 second. And so if that sounds kind of familiar, it should, because the period was time for one rotation, right? And then the frequency is how many rotations in 1 second. So you may be able to recognize that frequency is just the opposite, the inverse, the reciprocal of the period. Okay? So when we define frequency, frequency will be 1 over the period, or the period will be 1 over the frequency, either way. Now the units of frequency are called hertz. And we'll use this a lot more when we do waves and electronics and things like that, but it applies to circles as well, because hertz, the units of hertz, is cycles per second. Okay? So that's your SI unit for frequency. Okay? Not fundamental, obviously, it's not fundamental. It's a derived unit, but we can use that for cycles per second. All right? Now the last thing we want to do is we want to be able to link our angular and and rotation and the linear speed, okay? Because a lot of time we'll have the speed. So let's see if we can kind of figure that out. All right, so let's look at that. We know, ooh, that's not really what I wanted to happen. There we go. We'll just move that out of the way. We know that the linear velocity, v, equals distance over time, right? We also know that the angular speed or angular velocity, if we're not worried about the direction of our angular velocity, is equal to the change in angle over the change in time, right? Okay, well, if we're thinking about our angular displacement, if I can write that in terms of a distance, that will be very helpful here. Okay, now if we think about it, if I have a circle and I have some type of angular displacement, how far has it traveled? What is the distance? Now, we said that the angle will correspond directly to the number of radians if we're in radians. This is one of the reasons why it's so important that we use radians, not degrees. Okay? If I rotate through 1 radian, then my distance is the distance of 1 radius. Okay? Now, if I go through 2 radians, then the distance traveled will be 2 radii. Okay? And so I find out that the angular displacement is corresponded directly to the total distance traveled. Okay? So the distance traveled is going to be equal to the angular displacement, okay, which is in radians, times the length of the radius, right? Because if I go 1 radian, I go through 1 radius. How far is that? Well, it's the length of 1 radius. Now, if I take this and I put it into the distance, then what I have is that v equals theta r over t. And you'll notice that I there have theta t, which means that v equals theta t being omega, v equals omega times r. Now, this only works, remember we did this assuming that our angle was in radians, and that the total distance then was the length of a radius times how many radians we went through. That is the beauty of radians, and that, my friends, is why we use radians and not degrees, because degrees, I have no idea what the actual value of it is, other than the fact of the rotation of the Earth, which then isn't even exact, as we talked about. So, please use radians whenever you're in physics, unless it gives you degrees, in which case you can work with degrees. But use radians because that makes these formulas work. And we just found out that the velocity is equal to the angular velocity, or the angular speed, times the length of the radius. All right, let's go ahead and move on. Now, we've already established that an object in circular motion must be rotating, right? So let's consider a car. This is an aerial view. We're seeing a car. So here's my car. Yes, my car is a box, just like everything else, which is going counterclockwise. Okay? So at this point in the circle, you know that he's traveling in this direction. Okay? At some later point, he's going in this direction. Correct? Now, something had to change between here, between this one, and that one, because he has changed direction. Therefore, he must have accelerated. Okay? So in order to do that, we need to find out what the change was. So I'm going to take the first vector right there, this one. Okay? So that's what he started at. Okay? Now, he's going to have some kind of change, which is then going to result in this vector, which needs to have the same length, but now it's in the other direction. So this is the resultant vector. Okay? So this is the resultant vector. That's what he's doing after his acceleration. And then the first vector is his starting. So what is the change? Well, you take the initial, and then you add the change. So this is the change in velocity, and that gives you the resultant vector. So that change is defined as our acceleration. And you'll notice that over the course of that change, that is always pointing towards the middle. This is the average acceleration. So from the middle, it's pointing towards the middle. You can do this from any two places on your circle, and you'll find that the acceleration always points to the middle. Here, look at this. Let's take this one over on the side. Let's go from here to there. All right? So we have going down, and then we're going to add something on, and then in the end, he needs to be going this way. Okay, so what is the vector that needs to be added to our initial vector? What's the change to end up getting that final vector? Well, it needs to go in this direction. And you'll notice, you'll notice that that vector between these two, the average acceleration, is that one right there, towards the middle. From this, we can start to recognize that in circular motion, the acceleration is always towards the middle. This is how an object can maintain its constant velocity. We also talked about this with respect to energy. This is important because the force must be towards the middle. That's the only way that that thing causing the circular or rotational motion will not be doing work and will not be adding energy into your system. All right? So there we then have the idea behind the force causing this motion, or the acceleration. Remember, force, I use force and acceleration interchangeably because we know that force equals mass times acceleration. So if the acceleration is towards the middle of the circle, the force must also be towards the middle of the circle. All right? So from this, we can do centripetal acceleration. All right? Now, I'm not going to go through a proof of this formula. If you want to go through a proof of this formula, you can find one. There's a fairly good one on page 251 to page 252 of the Cambridge Sokos book. And they talk through a derivation of this formula. I don't think that the derivation of that is super duper important, nor do I really have time for it right now, as I'm trying unsuccessfully to keep the length of this video down. So therefore, we can now say, okay, well, I can calculate the acceleration if I know the speed. Now this, remember, this only works if the speed of the object is constant. If the speed of the object is not constant, it's going to require some stuff that we can't do right now because most of you haven't done calculus yet. So at this point, acceleration, we have to assume that the speed is constant so that it's actually going in a circle, not any type of ellipse or elliptoid or anything else weird. And then that you can see obviously that it's going in a circle because you would then have this constant radius here. Okay, so can we rewrite this acceleration in terms of the angular speed? Well, yes, because we know that our velocity is equal to the angular speed times the radius. So I can go ahead and put that in. So A equals omega r squared over radius, which gives us, when I work it out, I'll have omega squared r. Okay? Now, that's just another acceleration is again related to our angular speed. Okay? We can rewrite acceleration in terms of angular speed and velocity as well, if we really want to, right? Because we can calculate the velocity based off of the acceleration. So if I wanted to, I could say put this in. I could put, I know that omega, if v is equal omega r, omega is equal v over r. And so I could put v over r in for one of those omegas. And so then I would have omega times v over r times r, which would be omega v. So omega v would give me the acceleration. Now keep in mind, this is not angular acceleration, this is just the acceleration of the car going around the outside of the track. Now again, remember that the direction of the acceleration is always going to be towards the center of the circle, and that's going to be very important as we continue to go through. Alright, so let's look at another question. A ladybug is clinging to the rim of a spinning wheel, which is spinning counterclockwise very fast, and is slowing down. At the moment shown, what is the approximate direction of the ladybug's acceleration? All right. So first off, okay, go ahead and pause, think through, take a minute or two, and let's answer it. Okay, so first we have to recognize that if the ladybug is going in a circle, that there must be acceleration towards the middle. All right, so first we've got a component of acceleration towards the middle. Now, secondly, it says that it's slowing down. So it's going counterclockwise, so it's moving in this direction, which is not a force. It's not a part of acceleration, but that direction is moving. So if it's slowing down, it must have acceleration pushing it backwards in this direction. So if I take those two accelerations, one towards the middle and one slowing down, then the resultant vector is this right here. Okay, so that is the acceleration. Let's see, acceleration that way. And so it's got to be something such that it matches that. Well, it's obviously not straight down, so let's take that one out. It can't be this one that's completely going the wrong direction. So the question is it directly to the left or is it down? And I'm going to just make a guess that it's going to be B. All right? Now, if you said C, that's also okay. It actually probably depends a little bit on how much he's slowing down. I realized that I probably should have put the bug right on the side here. If I'd put the bug right on the side, then it would have very clearly been acceleration towards the middle, a little bit of deceleration. It would have had to have been C. So based off of where it is, I apologize. Go ahead, give yourself credit if you said either B or C, based off of the position of where the ladybug is now. All right, let's try another one. Pause the video, answer it, and then play. All right, so here's my take on it. I see that he's going at constant speed. So the same speed here as the same speed here. What's the difference between those two? Well, this is a circle with a large radius. This is a part of a circle with a small radius. So if I think about acceleration, because the question is when is the acceleration the largest, A equals V squared over R, correct? So if A is V squared over R and V is the same for both of them, this part's staying the same, so whichever one has the smaller radius is going to end up with a higher acceleration. So the smaller radius would be this position here from 3 to 4, okay? And so that's going to be my answer, is from 3 to 4, which would be letter B. Okay, larger acceleration. Now this should make sense if you're thinking of trying to go around a tight corner or taking a wide turn around a corner. Which one's harder? Which one requires more force from you or more work by gravity? Well, a tight corner is much harder to do, right? It's much more likely that you're going to slide because friction can't hold you. Friction's actually helping you here. I know we're often hard on friction, but friction is the reason we can do everything we can do. Without friction, we wouldn't be able to walk. We wouldn't be able to turn. Turning wouldn't matter because you can't walk. So, I mean, none of those things would be possible if we didn't have friction, which was pushing us forward or pushing against us as we push on the ground. So anyway, that'll be important to another slide coming up here in a second. So higher acceleration because of higher force, all because of that smaller circumference there, that smaller radius. It's not smaller circumference, smaller radius. All right? Next question. You've seen this, right? You've seen this ride. If not, go watch a video of it. It's pretty hilarious. People are in there. It spins around really fast. It goes zoo, zoo, zoo. And it goes around in circles as fast as it humanly can, or not humanly, as fast as they can get it to go. And the people feel like they're being pushed up against the wall. In fact, at some point, the floor drops out from under them. And you can see that here. They were against the wall. The floor has actually dropped out. And yet they don't fall. They are against the wall. The force between them and the wall is strong enough that they are not sliding down the wall. Okay? And so you can hang around. I did this once, and we were able to go upside down. We were able to turn ourselves upside down and all sorts of crazy things before it started slowing down, and we had to flip ourselves right side up so that we didn't fall on our heads when it stopped rotating. Now, very often, people refer to this as something called centrifugal motion. Okay? Centrifugal. Actually, I don't even know how you spell it. The reason I don't know how you spell it is because there is no such thing as centrifugal motion, right? What people want to say is that they are being thrown against the wall of this amazing ride, and there's some magical force that is pushing them back into the wall, holding them against the wall so that when the floor drops out that they do not fall. That makes absolutely no sense at all. What in the world is pushing them against the wall? Nothing. There is no centrifugal force. Okay? What is happening is when you're going around that circle, sorry, I can go back to the other slide. When you're going around, you're in this position right here. And as you go around, you want to continue doing what you're doing, which is going in this direction. However, the wall is getting in your way. When you go that way, you are running into the wall. The wall does what? Well, you push against the wall pushes against you in a perpendicular manner, which happens to be towards the center of the circle. That's why it must be a circle. Now, because the wall is pushing on you, what does Newton's third law say? Well, Newton's third law says that if you push against the wall pushes against you. If the wall pushes on you, you push against the wall. So you feel like you're getting thrown against the wall. We talked about this before when we talked about cars, right? When the car turns, you are not getting thrown against the door. The door is actually pushing on you and pushing you so that you accelerate at the same rate as the car, so that you move with the car. Otherwise, you would continue to go in a straight line, much as you were before. So it's very important to recognize that this object, these people on this ride, are going in a circle not because some magical force is doing it. It's because the wall is pushing them towards the middle. They want to keep going straight like this. The wall is always pushing them forward towards the center. Sorry, not forward, towards the center. All right? So the wall is exerting a centripetal force, not centrifugal. Okay, the same thing can be seen when you see like a satellite, right? That's why I have this slide here, is we're looking at this satellite going around the Earth. Well, what here is causing the circular motion? Well, there is no magical centrifugal force. What's causing it to go in a circle is just a normal everyday force, just like the wall was a normal everyday force. The satellite, if there was no other forces, would continue to go in a straight line forever and ever. Why is it not going in a straight line? Well, it's not going in a straight line because gravity is pulling it towards the Earth. So as it moves this way, it is falling towards the Earth. But the Earth, because it's curved, is now falling away from the satellite at the same rate. So when it's here, it's now moving in this direction. Again, gravity pulls it this way so that it stays in its orbit all the way around. There is a centripetal force. The centripetal force is just the force causing the circular motion. It is not a new force. There is no new force there. It's the same forces we've always looked at. It's gravity. It's the normal force of the wall, right? Up in this other one, it wasn't a new force. It was just the wall pushing on him, causing him to go in a circle. The centripetal force, you must recognize, is not a new force. I do not allow you to label a force as just the centripetal force. You can put centripetal force, but you must also tell me what the centripetal force is. Okay, if I'm doing this, yes, I can label this as force centripetal. But you will also label it as the force of gravity so that you know what the centripetal force is. I will not allow you to ever just label something as centripetal force, because then we start to have this belief that there are magical centripetal forces that make things go in circles because they want to. Okay? Doesn't happen. There must be a force there. No new forces, only the forces we've talked about up to this point. All right? Now, what I'd like you to do is take a minute and work out this question. The Earth has a radius of 6.4 megameters, that's times 10 to the 6th. Determine the centripetal acceleration experienced by someone on the Earth's surface at the equator. Okay, so I'm going to let you go ahead and work through that. You're remembering that acceleration, remember, equals v squared over r. You know the radius of the Earth. you should be able to find out the speed at which someone is traveling at the equator, right? Because you know how far it is around the Earth, right? The distance is just 2 pi r, so you can get the distance, and you know how long it takes to go all the way around the Earth. So you know the speed going around the Earth. And so you can do the distance over the time, which is your 24 hours, which you need to put into seconds. All right, I'm not going to work it out. I would like for you to work it out, and then check your answer with the answer I'll give you in just a second. All right, well, hopefully you got something around 0.033 meters per second squared. All right, so very small acceleration required to keep you on the surface of the Earth, right? This does have some interesting things. For example, that means that you would weigh less on the equator than you would on the North Pole. On the North Pole, you're not rotating very fast, so there's less acceleration needed to match the acceleration of the Earth. So, I mean, lots of interesting things that could come from that, but we're not going to go into those today. So, on to the next video. I want to talk about the physics of a turning car real quick. So, I've got a car, which is a box, as always, and my car wants to turn. Well, how does it turn? Well, the driver turns the wheel and magically it just goes, right? Well, no, of course not. When the driver turns the wheel, the tires turn, right? So the tires are now facing this way, depending on whether it's four-wheel drive or, well, yeah, just like that. So the wheels turn, okay? And then the wheels push backwards on the Earth, all right? Okay, wheels push backwards on the Earth pushes forwards on the wheels. As the car turns, there must be some kind of centripetal force. If there is no centripetal force, then the car would not be able to go in a circle. So what could be this centripetal force? Well, what force causes the car to actually turn? Well, that's right, it's friction. If there was no friction, when the car's wheels turned, it would just go in a straight line. So what that means is that a component of friction must be pointed towards the center of the curve of the car. That's very interesting because that means that friction is actually the thing allowing the car to turn. Now, why is that significant? Well, what would happen in rain or snow? What happens to friction? Well, friction decreases, right? Which means that this acceleration, this force, is more difficult to achieve because there is less friction, there will be less force, and therefore you will not be able to have as tight of a curve. Remember, it's A equals V squared over R, and if your acceleration decreases because you have less force available, less friction because of the snow or rain or whatever it is, if this goes down, then that means that the radius will have to be bigger. If the radius is too small, then it's going to require too large of an acceleration and you'll spin out. All right? Now, how can we adjust for this? What can we do? Well, the cool thing is we can actually do something. We're not completely at a loss. What we can do is we can put the road at an angle. So now I'm going to go to the side view of the car. So now the car is going into the page. Okay, I'm not going to do a box. Here's the wheels. We're seeing the back of the car, and the car is trying to go around this way, right? So the road kind of turns around. You like my three-dimensional drawing there. It gets smaller as it gets farther away. But he's trying to go from, right now he's going into the page, and he's going to turn over to the left so that he's moving to the left there. All right? So if there's not enough friction, one thing that you can do is if you know that it's going to rain a lot, or if you know that it's going to snow a lot, you put your road at a slight angle. How does that help? How does that help? Again, thinking of the circle coming from here all the way around, if you're looking from above, that means that you need more centripetal force towards the middle, usually supplied by friction. In this case, however, if we look at the forces on the car, right, you've got friction. Okay, when the wheels are turned, friction is going to help push it. You know, you've got friction. What else do we have? we've got gravity, which is pulling down, and then we've got the normal force, which is pushing that way. Usually the normal force just goes straight up, but you'll notice that now, because I've angled the road, the road actually pushes my car. It has a slight, or not so slight, depending on how much the road is curved, it has a slight component in the direction of the centripetal acceleration towards the middle of the circle. And that's why a lot of times, especially by high speed freeways and highways and things, when you exit the ramp and you have the road that's curving, it'll often be at a slant, because then the normal force assists with that curve. Okay? So from there, there's just one other thing I want to talk about. Which is this, vertical circles. And this will be the last slide for today. All right? Let's talk about an object going in a vertical circle. Everything we've done so far has been horizontal. So we've kind of been ignoring gravity. We've just been saying, okay, it's going in a circle. Either gravity's balanced out by the normal force, or just gravity is the centripetal force causing the satellite to go around the planet, whatever it is. Let's look at a vertical circle now. So we've got the Earth down here, right? You know it's the Earth because there is green grass. Okay, so I got my green grass, and now I'm taking a rock or something. So here's me. Yes, I am very skinny and awesome. So that's me, and I am holding a string, which of course has a really big rock on it, which I am spinning in a circle. Okay, so let's talk about this just for a minute. You got the idea, so I'm going to go ahead and erase my lovely picture so that I have space to talk about this. But you know what's happening now. We got the idea of what this looks like. Okay, so let's talk about here. The rock is here at the bottom. All right, so if the rock is at the bottom, what direction is the centripetal acceleration? Well, the centripetal acceleration, of course, must be up. Okay, I need a certain amount of centripetal acceleration. No matter where I am, if I want this rock to be going, if I want it to be at a constant speed, which is what I'm going to look at first, if I want it to be a constant speed, then I have to have a constant acceleration towards the middle, right? Now, in this case, what are the forces acting on my block? Well, you've got the force of gravity, which is down, okay, and that's constant. What other force is on this block? Well, really the only other force is the tension, right? But if gravity is down, how much tension do I need there? Well, it has to add with the gravity to end up giving me this centripetal acceleration. So it's got to be whatever that acceleration is, plus enough to oppose the gravity. So at this point, my tension is very large and towards the center, right? That will give me the acceleration needed to be towards the middle. Let's move our block over to the side now. Now my centripetal acceleration needs to be towards the middle, and I'm going to try to make it approximately the same size as it was before. Now, which direction is gravity and tension? Well, gravity's going this way. Okay, so we've got the force of gravity pulling this way. We've got tension pulling that way. Okay, now that means something. If it's just tension, we've got a problem. Because tension and this force of gravity will never balance out to give us this centripetal acceleration towards the middle. Okay? That's why when you're swinging a rock, you can't just leave your hand in the same place. And if you do, your fingers have to be moving. Because when you're here, you actually cannot be pulling straight horizontally when we're at this point. Okay? In order to end up with this acceleration, which is towards the center of the circle, then at this point, I need to be pulling up slightly. Okay? And so I have to have a tension pulling up slightly so that it balances the vertical component of gravity. Right? And that's the only way that I can keep this rock moving in a constant velocity. All right? Now when I get to the top, things again are going to change, right? Because now I've got my acceleration, which still needs to be towards the center, but I've got the force of gravity, which is pulling down like this. Okay? So if the force of gravity is equal to the acceleration at that point, wonderful. That means that there is no tension in the string. Now, this can cause a problem. If the force of gravity is larger than the centripetal acceleration needed, that means the force of gravity is going to be pulling down. The tension would actually need to push up, which it can't do. The tension is not able to push up to balance a larger force of gravity. So because of that, it's possible that if I don't have a large enough speed requiring a large enough centripetal acceleration, that my rock, rather than getting to the top, will not make it as high. Because it has to be at a point where the acceleration and the gravity are matched up, because the tension cannot offer that force. This goes into that question we looked at a couple of days ago in class, where we looked at one where it was a pendulum with a solid central pole, the rod, and in that case that was able to offer a force holding the object up in place, whereas the force of gravity and acceleration were both pulling down. Okay, the acceleration, was due to the force of gravity, the balance between the force of gravity and that acceleration. Okay, so some interesting ideas. Talk through this, look through it again, make sure that you understand what's required in order for this vertical motion to be in a circle. Now, what if I want there to be a constant tension? Okay, so let's just say for a minute that I keep a constant tension in the string. Okay, so here, at this point, I've got the force of gravity, and I've got the force of tension, and let's just say that they're balanced at that point. Well, they can't be balanced, or wouldn't be going in a circle, so my tension, let's just say, is just large enough to get it going through. So at that point, I'm going to balance out, and my overall acceleration is going to be a very small acceleration, right? Because that's the force, the centripetal force, balancing that tension and that gravity. When I get over to the side, okay, if I still assume that my tension is equal to what it was before, and the force of gravity is equal to what it was before, then my overall force is going to be the sum of those two, which is going to be something in this direction. And so now my acceleration is going to be in that direction, which is not going to give me a vertical circle. Okay? So we have to keep in mind that this acceleration, yes, must be, the acceleration has to be constant. That is not possible if I keep a constant tension here, especially if they're always going to the center of the circle. All right, so basically the point of that is I wanted us to talk through, look at the forces, look at the accelerations, understand that vertical circles are going to be a little bit more complex than horizontal circles are. Remember to include both the tension and the acceleration due to gravity. Okay, most of the time your object's going to be going fast enough that it's going to require both the force of gravity and the tension here to keep it going in this circle. Right? You can feel that when you're swinging your rock around really fast. It feels like the string's going to fly out of your hands. Well, that's because you are pulling on the string, and therefore the string is pulling back on you. Newton's third law once again. And so you feel that as it's going around. And so it's very, very common for this to be the case. All right? Where you have both gravity and your tension. And so let's just look really quick at that last situation. Let's assume right now that the force of gravity and tension are both giving you this acceleration, which is going to be that large now towards the middle. Okay? At the bottom then, so if I'm at the bottom, force of gravity is still the same. What has to happen in order for me to be able to maintain this same acceleration, that acceleration that is that large? Well, once again, remember, this has to balance out gravity and then still has to give that acceleration. So it's got to give that centripetal force plus balance out the force of gravity. And so this orange right here is going to represent the force of tension required. Okay, so just remember that. Kind of think about that as you think about things in vertical circles, that forces are going to be different in different locations in order to maintain that circular motion. All right? And that's all I'm going to talk about in this video. I know it's long. If you need to go back over individual pieces, go for it. You're probably ready that you can start looking at some problems, okay? Just pay attention to the fact that we're looking at centripetal acceleration, which is caused by forces. It has to be caused by some kind of force pointing towards the middle. That's all. Good luck.